Okay, so welcome to the AFMS Shear Flow Joint Seminar. So it's my pleasure to introduce Dr. Makoto Hirota. She's currently associate professor at the Tohoku University. He received his PhD from University of Tokyo in 2006. And then after having some research experiences at the Kyushu University and the Japan Atomic Energy Agency, then he got a position at Tohoku University, I think in 2013. So his main area of research is some mathematical physics studies of fluid flows and plasma flows. Okay, please go ahead.
Thank you. So it's very nice to meet you, everyone. So I'm Makoto Hirota from Tohoku University. And also I'd like to thank organizers, especially David-san, for giving me a chance to have a talk in this very interesting seminar. So today's topic is the Hamiltonian stability theory for fluid and plasmas. So this is a quite general topic, but I'm working on this problem many years. So let me give you some introduction. So first, we are going to discuss hydrodynamic stability. Maybe most of you are interested in this problem. So, but as you know, the fluid has an infinite degree of freedom, and also it's nonlinear dynamical system. So it's very difficult problem if you consider stability. And of course, nowadays we can use a supercomputer to perform direct numerical simulation, but it's still computationally high cost. So especially if you want to know the stability depends on the disturbance. So we cannot perform direct numerical simulation for every disturbance. So it's very high cost. So in many cases, we do some linear approximation and consider the behavior of disturbance around the base flow. So this is the stability problem. And this is the well-known incompressible fluid Euler equation. And this is the linearization. So we obtain the linearized equation for disturbance U tilde. So then we can solve the so-called eigenvalue problem for linear operator L. So this is so-called normal mode analysis. And sometimes we solve this equation directly by solving initial value problems to consider non-modal behavior. And another option is to perform WKB analysis and so on. So the stability of an individual flow U can be investigated numerically by solving this linearized equation. But however, this is the eigenvalue problem of a huge non-Hermitian matrix L. So this is infinite degree of freedom. So it's still not so easy computationally. So in my opinion, it is very important to understand the stability of various flows theoretically. So to understand this stability, we have to know the mechanism of instability and also the stability conditions. And to consider this problem, so I want to remind you that the inviscid fluid and plasmas are essentially Hamiltonian dynamical systems. So by using this general viewpoint, so we can discuss the stability systematically. And by observing this fluid and plasmas as Hamiltonian dynamical system, we can mathematically define the energy of disturbance. And by using this energy, perturbation energy, so we can obtain the stability condition. So this is the main topic of today's talk. And this is the general idea or introduction of energy of oscillation mode. So some oscillation mode around an equilibrium state has positive or negative energy. And in Hamiltonian mechanics, the modal energy is equal to the multiplication of eigenfrequency and the action variable. And this is a schematic view of oscillation mode in the phase space. So P and Q are canonical variables, and the Hamiltonian function or energy is the functional on the phase space. And if this Hamiltonian function is convex downward like this, the equilibrium point is here. And the oscillation around this point has a positive energy like this. So energy must increase like this. And this is the positive energy mode. But on the other hand, if the Hamiltonian function is convex upward like this, then the perturbation has the negative energy. So negative energy mode means that the perturbation decreases the energy of equilibrium state. Okay. And if, so this is the one mode and this is another mode, but if in total, the disturbance energy is positive or negative definite, we can prove that this equilibrium point is stable. So this is the general idea of stability condition. And this is the ideal case, but if there is some dissipation effect, or such as friction, only the negative energy mode is destabilized. This is also well-known theorem. So dissipation tends to decrease the energy of the system. So in this case, so negative amplitude of the negative energy mode increase due to the energy dissipation. So we can understand this mechanism intuitively. And also, if the resonance between positive and negative energy mode occurs, then it results in the instability. So if the energy is transferred from the negative energy mode to positive energy mode, so both mode exponentially increases due to instability. So this is so-called Klein collision of Klein resonance of positive and negative energy modes. So in this way, so various instabilities are understood by knowing the modal energy. So that's why the energy of eigenmode is very important. And this is the most, I think, the simplest example of negative energy mode. So let us consider the spinning top like this. And this is the two-dimensional dynamical system, Xi1, Xi2. And this vector represents the displacement of this rotating axis like this. And this is the dynamical system. So here we have the gyroscopic force. This is similar to the Coriolis force, like this. And also there is a potential force due to gravity. And if the rotation speed omega is very sufficiently fast, then this spinning top is stable, essentially. And it is well known that there are a positive energy mode and a negative energy mode. They are also called the fast mode and the slow mode. But if there is some friction, this slow mode, negative energy mode, will be destabilized slightly. And this is observed as the precession motion. And on the other hand, if rotation speed omega gets lower than this parameter omega g, then some resonance of positive and negative energy mode occurs. And then this spinning top becomes quickly unstable and fall down. And this is the example of the Klein collision of eigenfrequencies. So in the complex plane, there are neutrally stable mode, positive energy mode and negative energy mode. And if these two eigenvalues collide, it becomes unstable and damping mode like this. Okay. So the outline of the subsequent my talk is as follows. So first, I'd like to discuss the stability of inviscid incompressible fluid based on the previous Hamiltonian viewpoint. And basically, we will consider Euler equation. And next, we will focus on the stability of parallel shear flow or Rayleigh equation. And this result is essentially obtained by us in this paper. And next, finally, I'd like to generalize this theory to the extended magnetohydrodynamics. Maybe most of you are not so interested in the extended magnetohydrodynamics, but the formulation is quite similar to the Euler equation. So actually, section 1 and section 3 are both reviewed in my recent paper. So based on this formulation for Euler equation, we can easily apply this idea to the extended magnetohydrodynamics. Okay, so let me start with Euler equation. So I think everyone knows Euler equation like this. So I assume incompressibility. But here I want to transform or rewrite this equation into this form here. And omega is the vorticity. And here P, this P represents the projection to the incompressible vector field. So as you know, in the incompressible fluid, the pressure P is determined by solving the Poisson equation. So in this sense, this P is not additional dynamical variable. So we can, for example, we can substitute the solution of the Poisson equation to here. So we can eliminate P from the system. And such the operation corresponds to the projection into the incompressible vector field P. So this P means that we have already solved the Poisson equation. Okay. So I want to use this notation. And let us linearize Euler equation around the base flow, and the disturbance is V tilde. And because of the quadratic nonlinearity, we obtain two terms here and here. And actually, this is here and here, of course. But for later use, I want to define this linear operator L star V and A omega. And this is the definition. And these two operators are very important throughout my talk. So I will use this operator even in the extended magnetohydrodynamics. So that's why I defined these two operators here. But anyway, this is just linearized Euler equation. And now, so next I would like to introduce the Lagrangian viewpoint. And I mean, this is the flow map phi t, and phi t means that in this way, so the orbit of fluid particle like this, which initially located at the capital X like this. So this phi t is a mapping that represents the fluid motion exactly. And mathematically, it is called the volume preserving diffeomorphism group. It's a kind of D group. But anyway, so this is the fluid motion. So as you know, so there is a one-to-one correspondence between Lagrangian viewpoint and Eulerian viewpoint. So by taking the time derivative of flow map, we can obtain velocity field, Eulerian velocity field. On the other hand, by integrating the velocity field, we can obtain a flow map like this. And now, from this Lagrangian viewpoint, I want to introduce the displacement field like this. And this is actually first done by the Freeman-Rotenberg, 1960. And as you can see, so this is the original or unperturbed fluid orbit, fluid particle orbit. And let us perturb this orbit into here. So this is a perturbation. And generally, this is also nonlinear mapping, but let us assume the perturbation is very small. So in the first order, we introduced some vector field C like this. And this is actually the series expansion. So by considering this expression, we can calculate the perturbed velocity field by taking the time derivative of this one. And after some calculation, we can obtain the linear perturbation V tilde in this form. So this is the time derivative of C plus the Lie derivative of C. And Lie derivative defined like this. And in this way, so linear perturbation V tilde is represented by the displacement of a particle orbit. And this C is so-called Lagrangian displacement field. And let us use this C as a dynamical variable. And then consider again the linearized Euler equation. But before that, we can find that so we already defined three linear operators. This one A omega and L star V and Lie derivative. And by considering the very standard inner product for vector field, we can confirm that this L star V is the adjoint operator of Lie derivative. So that's why I defined this as L star V. And also, we can easily find that this omega is the anti-Hermitian operator or anti-symmetric operator like this. And another formula is non-trivial. So we can prove this mathematically. And this is the formula satisfied by these three linear operators. And if this holds if the base flow is a steady solution like this. So if we linearize the Euler equation around the steady base flow, we can prove this formula. And this is very important formula. And now we are ready to substitute this Lagrangian description into the linearized Euler equation. First, we obtain this expression. This is the linearized Euler equation. And by expanding this bracket, we can easily obtain this second order differential equation for C like this. And based on this symmetry and formula, we can confirm that this blue operator, this one, is anti-Hermitian operator. So this term represents some gyroscopic force, like the spinning top model. On the other hand, this blue operator, this one, is found to be Hermitian operator or symmetric operator. So we can say that this is the potential force. So in this way, so we can obtain a gyroscopic Hamiltonian system from the linearized Euler equation. And this is somewhat abstract notations, but by definition, we can rewrite this operator like this. So this is the Hamiltonian structure of a linearized Euler equation. And now we can define the disturbance energy or wave energy. So before that, so disturbance energy is not the square integral of the velocity perturbation. So this is a conventional. This is a conventional definition of perturbation energy, but this is not a physically correct definition. So actually, if we consider the original Hamiltonian H, which is the square integral of velocity field, but we have this series expansion, perturbation expansion like this. So if we calculate directly this, or expand directly this expression, we obtain the energy for base flow, and this is the energy for perturbation. So we obtain naturally additional term here, which is due to the second order perturbation. And this is usually unknown in the Eulerian description. And also this can be negative depending on the problem. So this is the difficulty, but because we already know the linearized system is this Hamiltonian system, so we can correctly obtain the expression for perturbation energy, H tilde, like this. So this is, of course, the kinetic energy of this system, and this is the potential energy of this system. And the gyroscopic force doesn't appear in the Hamiltonian system energy. And also by using this equation, we can rewrite the expression into this form. This is also a simple expression for wave energy. And for example, so if we substitute the plane wave like this into this definition of perturbation energy, then we can find that this wave has negative energy if its phase velocity is slower than the base flow speed. So if the base flow has a uniform flow U like this, and only the wave whose phase velocity is slower than U has a negative energy like this. Okay, now I'd like to consider the stability criterion by using this gyroscopic Hamiltonian system. So again, so potential energy is defined by this quadratic form by using this operator F. And first, if there is no gyroscopic force, if gyroscopic force happens to be 0, then the system is very simple. So in this case, we can obtain the necessary and sufficient condition for stability. It is that the potential energy is positive definite. So if and only if the W is positive definite, we can say that the base flow is stable. And in other words, so F is Hermitian operator. So if the maximum eigenvalue of F is negative, then we can conclude the stability. And this criterion can be applied to, for example, Rayleigh-Taylor instability of static fluid, and also various MHD instability of static plasma. So if the equilibrium state is static or no flow, as you can see, so this V equal to 0. So there's no gyroscopic term. So we can obtain accurate stability condition like this. But in general, so this gyroscopic force is present. So in this case, the stability criterion is a little bit difficult to obtain. But even in this case, we can say that W is positive definite. If the W is positive definite, the equilibrium state is stable. But however, this is only sufficient condition for stability. And unfortunately, so this potential energy almost always becomes negative or take negative value for some C. And because of some negative definite term. So this stability criterion is not actually useful for hydrodynamic stability. And so we have to find a more improved stability criterion. And this can be done by finding the conservation laws. And this is this idea was already proposed by Arnold, 1969. So this is called isovortical perturbation. And let us consider the linearized Euler equation again. And this is the gyroscopic equation on motion. And we can find that this can be factorized in another way, like this. And in this system, so we only have to solve this red part, like this equation. So the solution of this equation is just a restricted class of solution. So we import some constraint on the perturbation. And physically, this constraint is imposed by the voltistic conservation law. So if you look at this expression, so this is nothing but V tilde. So V tilde is generated by displacement C. And voltistic perturbation is generated by XC like this, similarly. So this means that the disturbance, this perturbation preserves the topology of vorticity. So this perturbation does not violate the voltistic conservation law. So, for example, if there is some vortex tube, so isovortical perturbation just deform, topologically deform this vortex tube. And if there is no vorticity outside of this tube, so it remains irrotational even after perturbation. And this is the isovortical perturbation. And by imposing this constraint, the energy of isovortical perturbation is expressed by this form, like this. And if this energy of perturbation H tilde is positive or negative definite, we can conclude the flow is stable. So because this is a constant of motion, so if this is definite, the perturbation is bounded by this constant of motion in some sense. And this is so-called Arnold's stability criterion. And formally, if we substitute the oscillating eigenmode like this, and this time derivative is replaced by the eigenfrequency omega, so the remaining part corresponds to the action variable mu, like this. So this is the normal form of energy of oscillation mode. And this is still a general stability criterion for linearized Euler equation. But if we focus on the one-dimensional parallel shear flow like this H tilde is reduced to this expression like this. But here I already introduced the wave number K along some flow direction. And yeah, we need some manipulation to derive this expression. Anyway, so by using this perturbation energy, so Arnold derived the very famous stability criterion. But first, he observed the same parallel shear flow in an inertial frame moving with some velocity u0. So then the velocity u is replaced by u minus u0 due to the Galilean transformation. And he concludes that if there is some inertia frame such that H tilde is positive or negative definite, then the parallel shear flow is stable. And this is actually more improved stability criterion than Rayleigh-Feucht theorem. So as you know, the Rayleigh's inflection point theorem says that if U has velocity profile U has no inflection point, the flow is stable. And the Feucht theorem is that if U has only one inflection point and this inequality is satisfied, we can say that flow is stable. However, these two criterions are sufficient condition. So, and this Arnold's criterion include these two sufficient conditions. So it means that this is the improved condition and more close to the necessary and sufficient stability condition. Okay, so in this paper, we try to further improve this Arnold stability criterion. And I want to briefly talk about this result. But the basic idea is to find another constant of motion, Q. And here we note that for any real analytic function f of c, this can be, for example, polynomial function of c, then we can define this quadratic form like this. And operator L is defined by this one. So this is the equation for isovortical perturbation. And we can directly prove that this is also constant of motion. So if f of L is just L, we reproduce the previous isovortical perturbation energy. Anyway, so for any real analytic function f, we can find this is constant of motion. So actually, so there are infinite number of constant of motion in this system. And also, we can observe that if this is the normal form of the energy of eigenmode. So this is the frequency times action variables. So in the case of this another constant of motion Q, so this expression is transformed into this expression, so f of omega j. But the action variable is essentially the constant of motion, so we can find that this is also constant of motion. So we obtain this stability criterion. So if there is some function f such that this Q is positive or negative definite, we can say that U is stable. But however, the problem is how to find appropriate function f. So you have infinite number of choices, so you have to determine this function f. And in order to answer this question, let me briefly introduce the continuous spectrum, the disturbance of fluid. So the fluid has an infinite degree of freedom, of course. So actually, there are not only eigenvalue or discrete spectra, but also continuous spectrum. So we cannot neglect the existence of the continuous spectrum. So actually, this is the difficulty of hydrodynamic stability. So such a continuous spectrum cannot be represented by the discrete dynamical system. And actually, this continuous spectrum corresponds to the integration of a singular eigenmode. And each singular eigenmode is localized along each streamline. So, for example, if you consider very simple linear shear flow like this, and put some disturbance like this. So naturally, this will be advected by the linear shear flow like this. And then this is a continuous spectrum, example of a continuous spectrum. So each disturbance is just advected by the base flow. But because of infinite degree of freedom, so this is not periodic behavior. So actually, this is called phase mixing. And because of this phase mixing, so the initial disturbance will be diffused or damped like this. But the energy does not dissipate in this system. So just phase mixing occurs. And this is a typical property of a continuous spectrum. So, this is the example of coffee, milk in the coffee. And if there is a differential rotation, I think the behavior of milk looks like this. This is also a continuous spectrum. Okay. And I won't go into the detail, but we have already calculated the energy for the continuous spectrum like this. So this is the energy for discrete eigenvalue, and this is the energy for continuous spectrum. And as I have shown, the continuous spectrum is actually the range of velocity profile U. So if there is a shear flow profile like this, the range of U corresponds to or occupied by the continuous spectrum like this. And this integration is along this line. So, and this is the energy possessed by the continuous spectrum. And also, we have shown that the sign of this action variable mu corresponds to the sign of U double prime. So if shear profile has curvature like this, U double prime is negative, and in this case, this corresponds to the negative energy continuous spectrum. On the other hand, if U double prime is positive, so it corresponds to the positive energy continuous spectrum. So only at the contact point of this positive and negative continuous spectra, a Kelvin-Helmholtz instability may occur like this. So that's why the unstable eigenvalue appears from the inflection point. And this is also similar to the Klein collision in the finite dimensional system. Okay, so based on this idea, we have generalized the Arnold stability criterion to multiple inflection points. And here, suppose that velocity profile has many inflection points, xn, and un is the velocity speed at the inflection point. Then we have to choose the polynomial function f of c like this. And then by choosing this plus minus sign, so appropriately, we can obtain this inequality like this. So we choose function f so that this inequality is satisfied. And then by choosing this function, we can change the signature of continuous spectrum, plus to minus or minus to plus. So, and after that, after this transformation, the sign of continuous spectrum becomes negative everywhere. So in the previous case, so there are positive and negative continuous spectrum. But by introducing another constant of motion q, so and if you consider the signature of continuous spectrum for this q, so it's always negative. So like this, the continuous spectrum is made negative definite. So then So we can prove again the stability condition, but we have proved that if U is a monotonic and analytic function, and actually this stability criterion is necessary and sufficient stability condition. So this is the most sharp stability criterion, I think. And this is the demonstration of this stability criterion. So actually, we have calculated the maximum eigenvalue of this operator, which is lambda. And so we will find the number of positive eigenvalue of this one. And then it corresponds to the number of unstable modes. So this dotted line shows the movement of lambda. So if lambda becomes positive, so maximum eigenvalue becomes positive, some unstable Kelvin-Helmholtz mode appears like this. So we can sharply obtain this neutral stability curve like this. And this is a little bit complicated example. So there are 3 inflection points here and here, here, and the energy changed like this. And in this case, some unstable mode appears at this inflection point and disappears at this point. So even in this case, so you can obtain the necessary and sufficient stability condition. And for details, so please refer to our paper. Okay, so I already explained everything. So I want to move on to the extended magnetic hydrodynamics, but this is just the application of the previous formulation, which I have already talked. And this is the extended magnetic hydrodynamics. So maybe you know the magnetic hydrodynamics, MHD, but MHD is just approximation. So this is derived by neglecting the Hall effect and electron inertia. And these are indeed very small effects, but sometimes not negligible in the collisionless plasmas. So in this case, we have to solve extended MHD, XMHD, and this includes the Hall effect and electron inertia. And this is also almost equivalent to two-fluid plasma, which is composed of ion and electrons. Anyway, so the equation is very complicated, like this. But here we have blue terms here. So this represents the Hall effect, and red terms represents the electron inertia effect. And without these terms, the system is conventional or standard ideal MHD equation. And for simplicity, I assume barotropic fluid. This. And these two effects are categorized by this small parameter, epsilon h and epsilon I. So here we observe epsilon h here as a coefficient. So this represents the magnitude of Hall effect. And after the normalization, so epsilon h is defined by the ratio of ion skin depth di to the representative scale length L. And also epsilon I is essentially the ratio of electron skin depth to the scale length L. And usually these two scales are very small, but we cannot neglect them. For example, in the boundary layer or in the small scale. And my motivation is to understand the linear stability of this complicated dynamical system, and I want to know how does it differ from the standard MHD. Okay, but actually, so I'd like to assume the incompressibility or simplicity. And in this case, the extended MHD is exactly equivalent to the two-fluid plasmas. And the previous extended MHD equation can be written as the Euler equation for ion and electrons. And originally, so this is a very complicated equation, but originally it is just the equation on momentum equation for ion and electron like this. So and this form is very similar to the Euler equation. But actually we have two momentum equation for ion and electron. So I and E represents the ion and electron. And this is the equation for canonical momenta, Pi and Pe. And the canonical momenta is, of course, the velocity field plus vector potential A. And the equation looks very simple, but actually the relation between canonical momentum and the velocity field is a little bit complicated, like this. So this is the, so there is the matrix operator M, like this. And this is the inverse of this curl operator, double curl operator. So we have to calculate some Biot-Savart integration to calculate this operator M. But we can find that this M is a Hermitian operator. And by taking the curl of this equation, we can obtain the vorticity conservation law. This is a very simple expression. And the canonical vorticity is conserved. So again, so we have two vorticity omega I and omega E. So the system is very similar to Euler equation. So we can apply the same formulation to the extended MHD equation. So the difference is only we have some complicated operator M here and here. Actually, we can obtain again the gyroscopic Hamiltonian system for extended MHD equation like this. And the variable is naturally the displacement field of ion and electron. And the definition is almost the same. And again, we obtain the very important formula if the linearization is done around the equilibrium state. Okay. But the remaining part is to the change of variables. So usually the MHD equation is written with respect to the velocity field V and electric current J. And these V and J are related to the ion velocity and electron velocity like this. So we just have to transform variables. And after the transformation, we again obtain a gyroscopic Hamiltonian system for Xi and eta. And here eta is the difference of displacement for ion and electron. But anyway, so this is the Hamiltonian system. So we can similarly define the perturbation energy like this. And if the potential energy is positive definite, we can conclude that the plasma is stable. Okay, I will skip this part. So, and similarly, we can impose we can define the isovortical perturbation even in the extended MHD. And again, we can factorize this equation to this form. And the solution of this part corresponds to the isovortical perturbation. But here we have two canonical vorticity for ion and electrons. So both of them are conserved in this perturbation. And this is the energy of isovortical perturbation. And we can again obtain the improved stability criterion. And this is just a generalization of Arnold's stability criterion for extended MHD. And this is a summary of my talk. So let me summarize my talk by showing this Venn diagram. So of course, the hydrodynamics is the most, the simplest, a small dynamical system. So, And we have many dynamical systems, MHD and whole MHD and extended MHD. And finally, two fluid plasma. And in its systems, we can derive, we can write the linearized system into this gyroscopic Hamiltonian system like this. And of course, it is very useful for solving the linearized system, but by imposing volticity conservation laws, so this dynamical system is further reduced to the isotropical perturbation, and we can obtain more improved stability criterion. And sometimes it can be necessary and sufficient stability condition. So this is the general approach of my study. So I think that's all today. So thank you for your kind attention. So if you have any question, please let me know.
Yeah, thank you for a very interesting talk. So yeah, we still have some time to ask some questions. If you have a question, just unmute yourself, or you may want to use some chat function. Let me ask one question.
Yes.
So earlier, you deduced some improved stability condition for simple shear flow with respect to lambda. So do we need some computation to find the stability, or is it easy to find this condition?
Yeah, actually, so we need some numerical calculations. So we have to find the maximum eigenvalue of this Hermitian operator. But this is a Hermitian operator, so some iterative method can be applied. So we can easily find the maximum eigenvalues. So actually we can use variational method to obtain this maximum eigenvalue. So I think it is much easier to obtain necessary and sufficient condition.
Yeah, at least it will be much easier than just solving a Rayleigh equation.
Yeah. The problem is Hermitian operator. Yes.
So is it possible to derive similar condition for MHD cases? For example, if you consider simple flow, can we deduce some stability condition?
Yeah, sometimes it's possible, but I think, yeah, it's very difficult. So, for example, so let me assume one-dimensional equilibrium state. So like this. So in this case, usually the continuous spectrum appear like this, and some part is negative and some part is positive. And if we already know this signature of continuous spectrum, so we can change the sign by multiplying this specific polynomial function. But generally, so some continuous spectra are degenerated. So positive and negative continuous spectrum are degenerated, overlapped like this. So in that case, we cannot change the sign independently. So that's one of difficulty, I think. And also, if we consider two-dimensional or three-dimensional equilibrium state, so it's more complicated. So it is really difficult to find such a special polynomial function.
I see. So, but is it possible to deduce similar form as this Q, even when we consider three-dimensional setup? I thought the difficulty in three-dimension is we cannot reduce this Q, or yeah. But yeah, it's also true that there's also difficulty in finding clean form for this F. Yeah.
So yeah, correctly speaking, so we can define Q even in the three-dimensional case. So we can find many constants of motion, but unfortunately, any or Q is indefinite. So we cannot make it positive definite or negative definite. So,
I see. Yeah, interesting. Any question? Yeah, just unmute yourself or maybe raise your hand in this Zoom reaction button. Yeah, this may be philosophical question, but yeah, when we include the viscosity, continuous spectrum would become some stabilizing mode. So do you say, I mean, we normally neglect such stabilizing mode. I mean, most of the fluid dynamicists ignore that mode. So do you say it's dangerous to do? I mean, do you think continuous
yes.
spectrum?
No, it's very good question. So today I didn't include the slide, but actually I confirmed that in the case of the, for example, the Hagen-Poiseuille flow or boundary, Brazil's boundary layer. So in this case, so U double prime is this one. So U double prime is negative everywhere. So in this case, the Kelvin-Helmholtz instability doesn't occur, but the continuous spectrum has negative energy. So if you include small dissipation, viscosity effect, so then some instability appears from the negative energy continuous spectrum. And this is actually the so-called Tolmin shifting wave, TS wave. And that's an example of so dissipation induced instability, in my understanding. And I think there are many examples of such.
So when we consider continuous spectrum, so we have some, well, one-dimensional object in complex plane, and TS wave is just one point. So maybe, yeah, most of the spectrum are destabilized, and one of those will be, stabilized, and one of those would be destabilized.
Yeah.
I see. Any questions from audience? Okay.
I really like this talk very much.
Thank you.
Thank you very much, Mr. Hirota. That was great. I really thought it was very aesthetic and very pedagogical presentation, and I liked it very, very much.
Thank you. I'm glad to hear that. Yes.
Yeah, it's very nice to see how symmetry of the equation can be used to deduce some meaningful result. Yeah.
And many people have tried to explain negative energy waves to me, and I never understood. And I still don't think I understand, but I understand a little better than before. Thank you so much.
Yeah. I think this is the simplest way to explain negative energy mode, I think.
Okay. Okay, so last chance to ask some question for speaker. Okay, if not, let's time for the speaker again.
Thank you very much.